And we have yet another cover page to this exam here, because this is such an old paper, 2010 this is, the MAT. We are only 1 year away from the 2009 My MAT paper, and that will be the last one I do. So this is the second to last one in 2010. Let's get straight into it. This is just the first 10 multiple choice questions. You can do this question without any work at all if you follow the patented R2 Drew 2 tip of just drawing a picture. This is this curve here, x minus 1 all squared, has roots at 1, repeated, and a y-intercept of 1. Just draw kx. Clearly, if k is positive, you're going to get a solution to these two things, regardless of how positive it is. You're always going to have a solution. If k is negative, sometimes you do, like this, if k is very big and negative, and sometimes you don't, if k is very shallow and negative. So we're looking for a solution where k is positive or bigger than 0 is fine, and also for some big negative values it's also fine. And that one looks pretty good, so we'll underline that one and be done. Of course, you can do this with algebra simply by equating the two things, checking for a discriminant of greater than 0, and of course you get the same kind of idea. You can run through this if you want to, but of course you'll get the same answer. But it's nice that we can do that without any actual work. Here, this is quite a nice question. You just need to spot that there are actually two sequences within this series here. There's the one that goes 1, 2, 4, 8, 16, and so on. And there's the one that goes 1, half, quarter, eighth, 16th, and so on. Once you figured that out, because there are two n terms in total, there are n terms of this and n terms of that. And of course, this is just a geometric series with first term a, ratio r, and n terms. So we can use the sum of a geometric series formula to do that with n equals n, r equals 2, n equals 1. Shove that into the formula. This is equal to minus 1, so it just flips these signs here, and we get this. And then here, same thing, a is 1, n is n, and r is a half. Shove that in. 1 minus a half is a half, so we double this top section here to get this. There's a bit of fiddling around to do with this. This is equal to 2 to the minus 1, which you can then multiply the indices for. And then this is 2 to the 1 times 2 to the minus n, so we can add the 1 to the minus n to get this. And now, of course, we just need to do this one plus this one, because the sum of these two series will be the sum of the total thing. So we add those two together. This makes a minus 1, sorry, this makes a plus 1. This we can turn into 1 minus n, and we get precisely this thing here. Very nice question. This one here, so this took me a while to see, but you can divide everything here by cos squared, because sine squared over cos squared is tan squared. Is tan squared, yeah, this is what I meant to say. This divided by cos squared, okay, so this cos cancels with one of the coses that you're dividing by, and this sine over cos equals tan, and then these cos squareds cancel. Now, before I do this, I just need to check that cos squared of x isn't 0. If it was, dividing by 0 is a problem. But if cos squared of x is 0, then cos of x is 0, which means this is all 0, this is all 0, and then I would need sine squared to be 0. But the times when cos x is 0, in other words pi over 2 and 3 pi over 2, are not when sine squared is 0. So this is fine. This must be okay. And now, of course, we have this. This is just a quadratic that I can factorize. You can use a substitution if you want to. And you have solutions at tan x equals minus 2 and tan x equals minus 1. And I'm being asked, how many solutions do these have between 0 and 2 pi? Well, if you draw the tan graph between 0 and 2 pi, how many solutions does it have with minus 2? Well, there are 2 of them. Don't know where they are, but there are 2 of them. And with minus 1, there are also 2 of them. Now, I do know where these are from exact values, but I don't care, because all I need to know is that there are 4 solutions in total, and so the answer is going to be 4. Good, D. So the first thing to say is this is sine of root x all squared. And whatever sine of root x is, when you square it, it's going to be positive. So y can only take positive values here. So this graph is immediately gone because it has y taking negative values, which can't happen. Anything squared is positive, or 0, so it can't be this graph here. The next thing I decided to do was look for the roots. So I set y to be 0. Square root both sides to just get this. And now when is sine of something 0? Well, it's when the something is 0, pi, or 2 pi. Or 180 and 360. I think I did this in degrees because modern math tests only do degrees, so if I have the choice to doing degrees, I think I'll take it. But of course, when I square both sides here, I get this. And now the thing about squaring numbers is they get further and further apart. Right, the distance between 0 and 180 squared is smaller than the distance from 180 squared to 360 squared. So the roots are getting further and further apart. They're not spaced evenly like this. And so it's going to be either this one or this one. And now it must be this one, because there's no reason for these peaks to change height. right? Sine, when you is sine of a function, a sine of something is between -1 and 1. When you square it, therefore, it's between 0 and 1, as I've discussed to get rid of this one. But it's always between 0 and 1. There's no reason for it to oscillate down here and then go up. It must be this one here. And so the answer will be B. E. So which of the largest? Which of these is the largest? So okay, let's go through these. This one is the most obvious, but I think I'll start here anyway. This is between 1 and 2 because I've just said A represents the question number. Because 2 to the 1 is 2 and 2 to the 2 is 4. So this must be between 1 and 2. This here is actually an exact value. 4 to the 1.5 is 8 because 4 to the 3 over 2 you'd square root for 2 and then you cube for 8. So 4 to the power of this is 8, so this is the answer, 1.5. This one here, now 3 to the 1 is 3, 3 to the 0 is 1, so this is between 0 and 1, which means it can't be the largest because these two are both bigger than it. And this one is likewise between 1 and 2 because 5 to the 1 is 5, 5 to the 2 is 25, so that's between 1 and 2. So it can't be this one, but we have to assess these three a little bit more properly. And when I say a little bit more properly, not really, I'm just going to go full engineer. Because what I can say is, let's just say 2 to the 1.5 is 2 root 2, which it actually is, because this is just 2 to the 1 times 2 to the 0.5, and 0.5 is the square root. Now, root 2 is, I know, about 1.4, so this is about 2.8. So what I'm saying here is that I need to use something a little bit bigger than 1.5 to get myself to 3, because 1.5 gets me to about 2.8, so I need to use something bigger than that to get to 3. So the answer to this is slightly bigger than 1.5. Which means this can't be the answer, because this one's slightly bigger than it. And likewise over here, do this exactly the same thing. Just say 5 to the 1.5 is 5 root 5. Root 5 is a bit bigger than 2, which means this is a bit bigger than 10. Which means I need to use something slightly less than 1.5 to get myself to 10. So this is slightly less than 1.5, which means this is the correct answer for the largest of the four. Good, this one here. So we split it into intervals, and which one is going to make an equal value here, if this is the function. Now if we split it into 4 sections, that's into quarters, so we have one at a quarter, one at half, one at 3/4, and one at 1, but this is going to be an overestimate, because this trapezium is exactly right, but this trapezium overestimates this shape here, because it goes from here to here. So that's an overestimate, so it's not a multiple of 4. Next, multiple of 8 would be the easiest one to do, because we can just shove in some more slits in the middle of these. So this is the 3/8 bit, because there are going to be 8 of them in total. So 3/8 is here roughly. It's bigger than a third, I think. Yeah, it is. But again, this is going to cause an overestimate there, isn't it? So the rest of it's fine, but this is an overestimate here. So multiples of 8 don't work. Multiples of 6. So okay, let's do a sixth first, and then a third, and then a half, and then what's the next one? 4/6, 2/3, and then 5/6. But again, you've got an overestimate here. So that doesn't quite work. And I mean, clearly the answer is 12, right? Because that's how we're going to get to this dot and to this dot with a common denominator of 12. So multiples of 12 will work. You could have jumped there pretty much immediately, I think. So yeah. G is one of those questions. We see lots of these questions in math. They've come up time and time again, where we just work a lot of things out. And it shouldn't take too long. F of 1 is 1. So F of 2, if we just use n is 1 here, is equal to 2 times 1, which is 2. F of 3, 3 is odd, so we must be using this rule. N is 1 gives you F of 3 here, so it's 4 lots of F of 1, which is just 4. F of 4 is twice 2, so we use 2 times this, which is 4 again. F of 5 is odd, you use N is 2, so you do 4 times F of 2, which is 8. 6 is double 3, so we're just going to double 4. 7 is odd, and we're going to use N is 3 here, so it's 4 times F of 3, which is 16. So that's our first value that's equal to 16. 8 is double 4, so we just double that to make 8. 9 we use 4 in here, so it's 4 times this, which is 16 again. 10 is double 5, so that's also 16. 11 we use 5 in here, 4 times this is 40, sorry no, it's not, it's 32. 4 times that is 32. 12 we double this to make another 16. 13 we put in n is, what, 6? 4 lots of 6 will give us 32 again. 14, we double this one to get 32 again. Just be super careful. It's tempting to think that you've passed all the 16s. But when you go to 15, you use n is 7, so it's going to be 4 times this, which is 64. But then f of 16 is even. It's just using double what 8 was, which is 16. And now, I think I can argue that I'm definitely done here with 1, 2, 3, 4, 5 16s. And the reason for that is I've just doubled this one. And now when you find terms, you either double previous ones or times them by 4. But I've passed this one now, so I'm only going to double or times by 4 things beneath it, which is going to be things bigger than 16. So I think I can say that I'm done here, and the answer is 5. This one's quite a nice one. It's almost like Tamura paper 2-esque, which of course are questions that I like. So you have this polynomial here. Which of the following statements? I mean, again, did I say this in question 1? R2 drew two things. I'm just going to sketch this. I'm literally just going to sketch it. When n is 3, this is a polynomial x minus 1, x minus 2, x minus 3 equals k. Now this is a cubic with roots at 1, 2, and 3, so it looks a bit like this. Roots 1, 2, and 3. Is there a value of k that this cubic never equals? Well, no, because whatever value of k you choose on the y-axis, you can always find a solution, because cubics essentially span the entire y-axis, because they go from down here up to here. Now quadratics don't, and that's about to be the next question. So A is false. There are no values of k for which I don't have a solution. Next one, if n is even, so I'm just going to choose n is 2 and choose the simplest quadratic I can, which is this. Now that looks like this. And this is saying that the equation has a real solution for any given value of k. Well, it doesn't, because I can just choose k to be negative down here, and then there's no solution, so that's false. And then this one as well. The equation never has a repeated solution for any values. Well, let's just look at the picture I've got here. If I move k down to here, there's a repeated solution, right? It has a solution, it has two solutions to k. Is that what it means by repeated solution, or does it mean repeated solution for x? Repeated solution x. Yeah, no, this would give me a repeated solution because x just touches it and goes down. So that there is a repeated solution. Like if I were to set up a thing that solves this cubic with this value of k, I'd have this repeated solution just like a repeated solution on an x-axis. So yeah, this is false. The answer is C, which I haven't even assessed at all. C makes a lot of sense because if k is bigger than 0, so we're only looking at k values up here, there's always a solution. Well, as I said, cubics always have a solution regardless. Quadratics, if you're just having roots at 1, 2, 3, 4, and so on, or quartics, or whatever, always start up here, end up here, so they're always in the positive section at least. It's just the negative bit they don't span, so this makes a lot of sense that C is the correct answer there. Okay, excellent. This question is very quick as long as you know the fundamental theorem of calculus. So you're going to differentiate I, so differentiate I on this side, differentiate on this side, just differentiating both sides. And now this looks a lot like the fundamental theorem of calculus because it is. What it says is if you differentiate an integral, and with some dummy variable here, between the limits of 0 and x, if you're differentiating with respect to x, then that's just f of x. So that's quite cool because it means that if this is just the function, I can just replace that with an a, and that's di by dA. But they're telling me di by dA is 0, so I'll set that to 0, move that over, 2 to the power 2 is 4, so a squared is 2, square root and we get the answer of root 2. Excellent, and the last question here, again, R2 drew two things only here. We're just going to sketch this. I'm literally just going to draw a picture to get this answer. How am I going to do that? Well, I'm going to reframe this inequality as not being this number is bigger than this number, as being when this graph, which is y equals a to the power x, is higher up on the picture than this graph, which is x equals cb to the y. I'm going to say this inequality is satisfied when this graph is higher than this graph. And now I just need to sketch both graphs. Now there's a few things to do here. Firstly, this graph looks different as when a is bigger than 1 or less than 1, as the hint shows in the question. When a is bigger than 1, it looks like a standard exponential, right? When a is bigger than 1, because when you have a number bigger than 1 and you raise it to a power, it just gets bigger. But when a is less than 1 and bigger than 0, which is implicitly said here, then it goes the other way. Then it falls down like this and goes the other way, because decimals like 0.5, when you raise them up to powers, become smaller. 0.5 squared is 0.25, and so on. So we've got our two graphs here, which look roughly like this. The sketching is terrible, but it doesn't matter. We're only interested in the positive section of the graphs, by the way. And now what does this graph look like? Well, you can rearrange for y, and you'll get a log, and that's fine. Or you can just say, well, you know what that graph looks like. if you just swap the x and the y, we know what this graph looks like, mostly because we've just drawn something basically the same. If b is greater than 1, it looks a bit like this. It's stretched up a little bit according to what c is, which is positive, so we don't have to worry about it being negative down here. C is positive, so it might be flattened or stretched up. It doesn't really matter to us. It looks a bit like this if b is greater than 1. And now, if you know what this graph looks like, and you have a graph where the x and the y have just swapped over, then that's always just a reflection in the line y equals x. So this black graph here is just a reflection of the blue graph in this line, which will look a bit like this, which is of course a log function, which you would get if you just rearrange that for y. So that's fine, but we'll get a log function. Now, looking at this picture here, for positive values of x, the red graph is always above the black graph. And so there are not finitely many positive numbers, x and y, that do this. There are infinitely many, because it's always above the black graph. So this is not the case we're looking for. What about this case though? Well, let's keep b greater than 1 and just shove it on here. And what we see is b, the black line, is above the red line here. So the red line is only above the black one between these two in this section here. Again, we don't care about the negative areas. So it's just here. So it's finite. There's a finite distance for which the red one is above the black one here. And so this is the answer here at D, when a is less than 1, b is greater than 1, because there's a finite number of positive things for which the red one is above the black one. And that's the whole paper. Thank you for watching. I'll see you next time.